and oh boy, will be recorded. So if hopefully everything goes according to plan, and if I need to somehow change computers in the middle of it or whatever, hopefully everything works all right. So great. So I'm talking about this joint work with Corey Jones and David Reuter, basically talking about G cross-braided categories from a three-categorical perspective. And it just appeared, it was just published open access in the Journal of the London Math Society. So this is this DOI here, means you can find that, or just, if you go to my website, you can find an easy link there. So what this work was motivated by is the fact that G cross-braided categories, they arise in many physical and mathematical contexts. And why is this happening? Okay, so in particular, they arise from global symmetries in 1+1D chiral conformal field theory. So this is work of Muger, who showed that these things arise there. Also, they arise as symmetry-enriched topological orders in 2+1D topological phases. They arise in extension theory of fusion categories. This is the ENO extension theory. And they arise actually as invariants of 3D homotopy TQFTs. And so the question is, well, why? Why are they arising in all of these different places? And here we have one explanation of that, I think, is this theorem that we proved this year, which says that G cross-braided categories, these things are the same as, there are three categories. So here's this C, it's this thing over here, C prime, three category C prime, together with a one surjective three functor from this thing called BG. What is BG? Well, this is called the de-looping of the group G. This is a category, it has one object, and then it has a G's worth of one morphisms, and it's really just a one category. But I'm talking about a three category from a one category, a three functor from a one category to a three category. That just means that I take this one category and I think of it as a three category trivially by just adding identities on the top to make it a three category, and then I look at a three functor. Okay, so these this is an equivalence here. Now, one of the subtleties here is that if I look here on the right, this is a four category, and this thing on the left, this is a two category. So you might think, well, wait a second, this doesn't quite type check, but really the statement is that this four category is equivalent to a two category. So this means that the four category only has identity, like it's equivalent to another four category that only has identity three morphisms and identity four morphisms. So you can just lop them off without losing any data, and you get a two category, and that those two categories are equivalent. That's how you want to think about this, okay? That's essentially the idea. So this four category, this thing here, we're going to call it 3cat G, okay? And so how do we go about proving this? Well, really, this is kind of hard to see in this fully weak form. So what we do is we pass to, first of all, we go to strict G cross-braided categories here. And these are equivalent as two categories. So the objects are strict G cross-braided categories, and then you have the normal weak functors and the weak natural transformations. And this is due to Galindo in 17 to make this strict. And what we do in our paper is we find this strict, I'm going to call it strict G-pointed three categories. So the idea is that you're taking this kind of thing with this one surjective three functor here, and you can kind of strictify this thing to a thing I'll call 3cat G strict, okay? And then we construct an equivalence here between these things. Okay, so I'll say a little bit more about this whole process of the strictification and doing that later in the talk. But this kind of gives us an answer to why all these four different things, why G cross braided categories are arising in there, and the answer is three categories. Okay, that's really the answer here. So the point is here, these 1+1D conformal field theories, these form a three category by work of Bartels, Douglas, and Enriquez, and in a series of papers. These 2+1D topologically ordered phases, these form a three category. Now, there are many ways to see that these things should form a three category. One way that I like particularly is that if you think about 2+1D topological orders with a fixed anomaly, so there's some kind of anomaly, which means that really these 2+1D topological phases are living on the boundary of some kind of 3+1D invertible TQFT, and that 3+1D invertible TQFT is you can think about that as that's like the anomaly. Now, if you fix the anomaly, then you have this three category of topological orders with that fixed anomaly. This description appears in recent work of my student Peter Houston, Fiona Burnell, Corey Jones, and myself. And that's not in alphabetical order because it's in the physics ordering. Peter is first author on that. And then this extension theory of fusion categories. Well, fusion categories, these things form a three category, right? And there's a lot of different references for that. One would be Hogsang, one would be Jensen, Freud, and Scheinbauer, and another might be the work of Douglas, Schomburg-Pries, and Snyder that you might think about for the three category of fusion categories. Okay, I'm not going to say anything about 3D homotopy TQFTs, but the idea is if I have a three category and I pick my favorite object in a three category and I have a G action on that object, whatever, basically this idea of a G action is the same thing as this three functor from BG into this, that this BG selects at this point, it selects this object, the G's worth one morphism selects the G action, and then you kind of put it into our machine and poof, out comes a G cross braided category. So this gives you a uniform construction for all the different G cross braided category constructions out there. So that's what this theorem does. It kind of puts everything under one roof. Any questions? That's kind of like the major overview about the result.
Sounds good.
Okay, let's keep going. So let's try to understand how all something like this might be true. There's this periodic table of higher categories due to Baez and Dolan talking about k-tuply monoidal n categories. So here, this level 0 here, zero monoidal 0 categories are sets, zero monoidal 1 categories, and zero monoidal 2 categories are 2 categories. Okay. And we're not going to really worry about the 3 category level because really we only ever need to talk about monoidal 2 categories for our story today. But then, a monoidal set, that's a monoid. A monoidal category, we know what that is. And we know what a monoidal 2 category is. So this is this one, when K is 1, that's a 1 monoidal n category. For a 2 monoidal, whatever category, well, I'm going to start over here with this is the notion of braided tensor category here. Over here, this would be braided tensor 2 category. But when I'm at a monoid level, I'm all topped out. Essentially, the only thing I can ask for that monoid is for it to be abelian. And then when I'm thinking about thrice monoidal 1 categories, at this point, I'm really just topped out again. So I should really put this in another color because this one is a property. So I'll make this, that color. Great. Here, this is the notion of a symmetric tensor category. Down here, this will be symmetric tensor 2 category. But there's still this one other thing here. Here, this is a selectic monoidal 2 category. So all of this is structure up until the very top where you get property. So these are, it turns out you can actually extend this down to -1 and -2. You can talk about -1 and -2 categories. And up here, you actually put truth values. This is a really cool story that you can actually think about negative categorical thinking. And it's really good when you're doing stuff in higher categories to try to always go down one level first, right? That's like a really good idea to think about, oh, what happens if I go down one categorical level? And so you can even go down from 0 to -1 and -2 and try to think about what that even means. And that can be very helpful when you're doing higher category theory. And G cross braided categories fit into this story, right? The idea is that you can think about n plus k categories with this G surjective functor for different values of G, what this G might mean. So when G is empty, this is like, this is this idea of when k is -1 and n plus k is 1, then I'm getting, I hope I have the numbering right here. For some reason, it doesn't quite look, it looks a little weird to me, but I think it should be okay. Let's see, n plus k is 1. Well, all my screens are like totally messed up, but I think I'm just going to trust myself that it's probably okay. And we're going to keep going. Okay, so either it's correct or I have an off by 1 error, and with higher categories, that happens. So if you equip these higher categories with this pointing, so this G surjective function, you should think of it as like a pointing, and you think about the resulting structure that happens, often you get some kind of dimensional reduction happening. So if you're not pointing at all, you get 1 categories, 2 categories, and 3 categories. When I start pointing by something, like an actual point, that 1 category goes down to a monoid. This 2 category goes down to a tensor category, and this 3 category goes down to a tensor 2 category. And it really means that if I think about the collection of 2 categories, say, really I'm getting just the collection of tensor categories instead of the collection of 2 categories. So 2 categories form a 3 category, but tensor categories only form a 2 category. So when I equip with this pointing, I'm getting a lot less structure. And I'm going to say a little bit more about that later in the talk, okay? And kind of give this overview about how that works. When I'm pointing by BG, really, at this level, this is equivalent to a normal subgroup of G at this 1 level. At the 2 level, this is a G cross monoid. And over here, this is where we get our G crossed braided category. And what one could do is you could think about this, the script G could be something more interesting, right? So instead of using BG, this delooping of the group G, just to remind you, this BG is, it's just a category with 1 object and a G's worth of 1 morphism. It's just a group worth of 1 morphisms. Instead, that's like a homotopy 1 type. Instead, you could instead of thinking about BG there, you could think about higher homotopy n types. You could think about some kind of you could think about like pointing by a 2 group or a 3 group or something like this. And this, when you're thinking about extension theory, in the extension theory, there are all these things like cocycles and obstructions, and sometimes the obstructions don't vanish. And that's when the obstructions don't vanish. That's when you could really replace something with some other kind of 2 group or something, or 3 group or whatever, depending on what thing you're looking at. And you should have a perfectly good theory that works through there. And that would be an interesting thing for somebody to go through and work out. Okay. Cool. So let me say a little bit about how we prove this main theorem here. Okay. This idea about how we're going to take something strict here and construct going that way. And then we're going to talk about how we take something here and construct something going the other way. And we're just going to do that on the level of objects. I kind of want to explain how that works on the level of objects. And then the rest of the talk, I'm going to talk about something a little bit different that has to do with this, like strictify both sides and then try to get an equivalence in the middle. But I want to go down a categorical level and explain something in a lot of detail to really see, like I said, in higher category theory, just go down a category level, and then you'll really, I think you have a better chance at understanding something. So that's what I'm going to do after I talk a little bit about how these constructions go in both directions. Okay. All right. So in order to do that, we should talk about the gray monoid graphical calculus. So a gray monoid, these things called gray monoids, these are semi-strict monoidal 2 categories. That's what this means. So there's a theorem of Maclane's coherence theorem or Maclane's strictness theorem, it depends how you want to think about it, that says every monoidal category is equivalent to a strict monoidal category. And that strict monoidal category has identity associators and identity uniters. And, I remember first going through this, and because I originally learned everything through planar algebras and not tensor categories, I got so confused. I'm like, wait, I'm using planar algebras. Everything's already kind of strict, but like there's supposed to be some associator. And, there's this wonderful question of really Sebastian Paucu asked this question on Math Overflow, and it was like something I'm like, oh, I remember this. I remember like being super duper confused about this, and it's a really, yeah, it's really quite frustrating. Now, when you go up a category level to monoidal 2 categories, unfortunately, the theorem that you want just fails, right? It's not true that every monoidal 2 category is equivalent to a strict monoidal 2 category. It's just not true. And the problem here, you can already see it when you get to when you see braided tensor categories. So remember, if we're looking up here, if I'm thinking about these monoidal 2 categories, I can just look here at, there's essentially, these braided tensor categories can be thought of as particular kinds of monoidal 2 categories because they're on this diagonal here. And there are certain kinds of 3 categories. So it's a 3 category. If I have a 3 category with one object, I come down here. If I have a 3 category with one object and one morphism, I come down here to braided tensor category. And so these braided tensor categories are particular examples of these monoidal 2 categories. And you can see that you can't be strict because this braiding is non-trivial. So let's explain what's happening there. Okay. So gray monoids, these semi-strict monoidal 2 categories, have a graphical calculus. So how should you think about this graphical calculus? Well, here, these are objects, right? These A and B are going to be objects in my gray monoid. These X and Y, this is a one morphism here between these 2 objects. These are parallel one morphisms. They have the same source and target. And then to write a 2 morphism, we're just going to write it as an arrow going from here to here. Now, the way you can also think about it is there's this graphical calculus for 2 categories, which I would draw on a sheet, okay? And here I would think about F as living as a coupon on this sheet. So here's A, here's B, here's A. A is labeling this sheet over here, right? So A is over here, B is over here, right? This is B. Okay, this string here, down here, I'll just put some more color in because that'll be great. This string here is X, this string here is Y, and I'm kind of reading upward on this sheet, but I've kind of drawn it at an angle because I'm looking at it, my viewpoint is from the side. So I've got a 2 category that lives on a sheet, but the sheet looks like this, and I'm going to look at it from this side, okay? If you're looking at my picture, yeah? Does that make sense? Got a sheet, and I'm looking at it from the side to see the actual 2 category graphical calculus. And for a gray monoid, I'm going to look at it this way. I'm going to look down, and I can't see inside the sheet, yeah? So if I look at the side, I see the whole sheet. If I look on top, the sheet is I'm only seeing part of the sheet. The sheet is going underneath there, yeah. And so as I'm reading upward this way, this is exactly this morphism F. Okay, so that's how we're thinking about this graphical calculus. Yeah. Okay. Please stop me at any time if you have any questions. Okay. So that's the 2 category part, and that 2 category part is strict. Okay. So the underlying 2 category, this is strict. But then we're going to get to this monoidal structure, which is not, it's as strict as it possibly can be, but it's not strict. So the idea is that I can take 2 of these 2 category sheets and I can stack them together. And that's what this is here, right? So this is an A sheet. That's an A sheet here, right? So this is this A sheet here. And this here is this just, here I have B, here I have C, and I have X. That's what it looks like from the side if I were to tilt my head. And I'm stacking those 2 sheets on next to each other. Yeah, this is left tensor product, and left tensor product with an identity is strict. Okay, so this left tensor is strict on the object. So this is this functor LA, which is a strict 2 functor in a gray monoid. This here is R sub C, which is also a strict 2 functor. Okay, so I have these LA and this RC. They're strictly associative. They commute with each other strictly. So there's really nice things there. The difference, the whole interesting part about a gray monoid is that if I define X tensor Y for one morphisms, I can't put them on the same line. I have to draw one on the top and one on the bottom. So if you're familiar with planar algebras and you're thinking about like Jones planar algebras and how you get a planar algebra from a subfactor, you write something in a standard form and there are critical Y values. Well, these pictures have critical Y values and they're not allowed to cross. Okay, so also, I guess if you've learned about parafermion planar algebras, Chung-Wei has a lot of research there. Again, you're not allowed to cross without something interesting happening. Yeah. So this picture on the right, even though topologically it looks the same, if I were looking at two pictures in two categories, these would be the same. These are actually pictures in a monoidal 2 category, which is actually a picture in a 3 category. These are different. So they're not the same. They're not equal. There's actually an isomorphism between them called the interchanger. Okay, the interchanger or the exchange, yeah, interchanger is what I like to call it. And you can think about this as being, when I'm looking at it from the side here, so here, I've got these two sheets. This one has an X over here and a Y here. If I look over here, this one has an X over here and a Y here. So really what's happening is that this X and Y string are braiding. Uh-oh, for some reason I've saying what's happening? Can you still hear me?
Yes, we can hear you, but the screen
has stopped. And why did that happen? Yes, for some reason it just stopped sharing. I don't know what happened here. Let me just hit stop share and I'll reshare. I don't know what's going on here. Okay. And we're back. Yeah. Okay. So the idea here is I've got this Y string and an X string. Of course, they're on these sheets, right? Here, this is an A part here, and then there's a B part here, etc. There's a C part here and a D part here. That's labeling these. That's labeling these parts of the sheet. You know, whatever. And what's happening is these two strings are actually braiding past each other. This interchanger looks like a braiding. All right. And in fact, here's an example. If I take a strict braided tensor category, that's a gray monoid with only the identity object. Okay. So if I have a gray monoid with only the identity object, then what I can do is, okay, if there's only the identity object, then I have the objects in the braided tensor category. These are X and these are Y. And over here, I have X and Y. And there's an isomorphism which goes between them. I could call it phi, but typically you would call this beta for the braiding. And if you think about what's happening here, you see that this is exactly what's happening is the Y particle is going up, the X particle is going down. And so if I'm thinking about what it looks like from the side, the Y particle is passing in front of X. This is the braiding on the nose. And so we see that, you know, if I have a braided, even if I have a strict braided tensor category, the braiding is not the identity, right? That would be ridiculous, yeah? Every monoidal category is equivalent to a strict monoidal category, but I can't strictify the braiding too. That would just get rid of too much structure. So this interchanger is just a part of life. It's what happens when we're working in 3 categories. Interchangers just happens to be around, okay? Because it's essentially, you should think about it as the braiding. Any questions about this? This is just kind of our, this is the pictures that I'm going to use to do these constructions on the next page. It's all right. I've got a 2 category. It's strict 2 category. Look at it from, if I'm looking from the side, I see the whole 2 category. I look at it from above. That's the pictures I'm drawing. And I just have I have a way to stack them. And that's kind of looking on. Okay. All right, so let's talk about this construction and how it works. So first, we're going to start with a gray monoid whose objects are G. So this is like kind of the strict version. So I have a gray monoid, a G's worth of objects. And from this, I want to construct a G cross braided category. How can I do that? Well, CG, we're just going to define it to be, so the thing on the left is going to be script, this is going to be script C. And the thing on the right, we're going to call it just regular C. Now, a G cross braided category has G components. So I'm going to define the G component for every G. And let's say it's just C from 1 to G. And this is a 1 category. And then, if you're working linearly, then the actual G cross braided category you would do is just you'd take like kind of a big direct sum of these CGs, and that's the kind of thing that you would take as your G cross braided category. Or, what we do in the paper is just kind of do a nonlinear version of it, but it doesn't really matter. You could just take these C sub G's, take the direct sum. That's your G. That's going to be your G cross braided category. But now we have to give a monoidal product. So what is X tensor Y? Well, X is some HOM. So X will live in the G component, this will live in the H component. So X is a HOM that looks like this. Y is another HOM that looks like that. And I have some sheet labeled G and some sheet labeled H. And a gray monoid is strict. So if I take the sheet labeled G and the sheet labeled H and I put them next to each other, that just is the sheet labeled GH. Just because that tensor product is strict on that level of objects. So this happens to be a HOM now. This is a HOM. This lives in C from 1 to GH, which is exactly CGH. So if I have this tensor product from CG tensor CH to there, right? That's how tensor works. Yeah, that's how a tensor works for a graded category. Great, it seems to be working. Then there's this G action. What does it mean for G to act here? Well, what we do is we take that X morphism and we're going to put this G strand around the outside. So G is here. Maybe you can think about it as being oriented. And we're going to wrap the G strand around the outside. Okay. So because we have a gray monoid, this is a perfectly good thing to do. And this defines for us, it gives us an action. G is now going from C sub H to C GHG inverse. And that's how the G action is meant to go in this G cross braided category. Finally, I have to tell you what the G cross braiding looks like. Well, essentially, what is the G cross? Well, I'll draw the picture first. And great. So I've got an X and I have Y. This guy's labeled G and this one's labeled H. Well, what I'm going to do is I'm going to apply this interchange isomorphism to bring X downward and bring Y upward. And then what I'm going to do, first of all, I'm going to draw this G in blue because we did that last time. It was blue. Then all I'm going to do is I'm going to use strictness here. I can just move X to the right at no problem. Like there's no problem with me moving it to the right. It's only the up and down critical values where there's going to be a problem. And it looks kind of like cheating, but I assure you it's okay. The idea is this is the same thing as putting Y here, X here. This is labeled by H. This is labeled by G. And I can put another G, H, G inverse here. I guess, oops, G is, I don't know why I've chosen this as the orientation. It was a bad choice, but yeah, let's just get rid of the orientation. I'm just gonna write labels on these strings so that it doesn't, we just won't get confused because there's labels on all the strings. Yeah, okay. And why does this make sense? Remember, those sheets, I have this strict tensor product there. So if I just kind of smush it all together into one sheet, then I'm getting the same picture on the left, okay? But you'll see that this is exactly here. This is G of Y, tensor X. And over here, I have X tensor Y. And that's what the G cross braiding does in the G cross braided category. It goes from X tensor Y to G of Y tensor X. And this works when X here is in the, that one has to be in the G graded component here, okay? So on the left, we're in CG, maybe box times CH. On the right, we're in CGHG inverse box times CH. CG. And that's what the G cross braiding looks like. Okay, so that's a construction. I've told you what it is, and then you just have to go and check all these coherences, and it's a huge pain in the butt. But we have some really nice ways to go about, nice graphical notations to help us check all these coherences, and you just do it. So we kind of were doing all these proofs right when the pandemic first started, and when everything kind of, first shut down. And so this was like, I would just kind of do a coherence proof a night. That's how I kind of kept my sanity for the first 3 months of everything. I would just kind of like be like, all right, I'm going to do one coherence proof a night. And it was nice. Okay. Now that's the direction one way. Any questions about that? So I'm going to go for the direction the other way in a second. All right, let's go the other way. So now I'm starting with a G cross braided category, and I have to define a gray monoid. And really, this is really following, I believe, work of this is work of Sean Sweet. And we end up, doing the rest of the higher categorical version of this, but I believe this construction, one of these constructions is due to Sui, and I can't remember which one it is actually, whether it's the first one or the second one. But one of these is due, I believe one of these constructions is due to Sean Sui. I should make sure to say that. I know Elong's there. Maybe Elong knows. I don't know. Anyway, so
yeah. So
you don't know?
no, I forgot. But one of
Oh.
his, I remember he wrote some paper on it.
Yeah, he definitely has this. He has this very nice paper on it. I just totally forgot which one it is. I hope he doesn't mind. So the next one, we're just going to say how this works. So we have to define the Hom space from G to H, or the Hom category from G to H. So it should be a whole category. And how are we going to go do it? I'm going to do it. I don't know if this is this. I'm going to do it guided by, it's going to sound kind of funny, but I'm going to do it in a very subfactory kind of way. In my opinion, I think really subfactory. And so I'm thinking Kuhn's algebra endomorphisms. And that's kind of the rule that I'm going to use in order to write down things. So hopefully this means something to you when I write down what it's supposed to be. So if I'm writing down Homs from G to H, well, in your mind, you could think, okay, well, this is like, because I want to write down something strict from it. I want to write down, well, I could write this as HG inverse and kind of peel off this G sheet. This is Hom space, and I'm going to identify this. This is the same thing as just getting, I'm going to say drawing a sheet to the right is the same thing as drawing nothing. And so I just want to define this as CHG inverse. And that's a category. So I'm going to say this Hom category is exactly CHG inverse on the nose. Okay? So I'm using these pictures to kind of guide me to say, how do I do it? I'm kind of drawing this picture. I'm thinking about like Kuhn's algebra endomorphisms. If I have an endomorphism and I draw a strand to the right, it's the same thing, nothing changes. So it's the same category, nothing changes. Okay, how do I compose? Well, I can think about this as, here I'm just drawing a little yellow bubble and a blue bubble as the morphisms. So there's a yellow bubble here, here's a blue bubble here, and I'm going to do the same trick. I'm just going to, here I'll put a K, here's an H inverse, here's an H, here's a G inverse, and then I can put a G here. Yeah. So it looks like composition. This is just tensor product in C. This is circ in my, this is like one this is the, what is this? The one composition inside my gray monoid is just going to be my tensor product. in my G cross braided category, because the picture tells me I should just be able to do that. So I just define it that way. Great. Now I have to figure out, how do I tensor with the sheet on the right? Well, tensoring with the sheet on the right isn't supposed to do anything, right? So really, I should be able to move this over. Here I have a G sheet and a K sheet, and here this is H and G inverse. So, you know, just do nothing. It's the identity. But tensoring with the sheet on the left here, well, let's think about what that looks like. This is G, then I have K H inverse, but then I can write an H sheet here. But then I can do this trick that I did up here. If I have this sheet on left of something like this, I can move it that way and then just wrap it, okay? So this is the same thing as KH inverse. I wrap this with this G sheet here, G inverse, but then I've got to put a G sheet back and an H sheet here. So I get exactly, this is basically, you have to use the G cross braiding. In order to implement this this fusion on the left. Okay, so it's the G cross braiding applied to the I have to act G on it, and so I'm going to see GH K inverse G inverse. The G action is acting there. Sorry, the G action. You have to use the G action, not the G cross braiding. The G cross braiding is this interchanger. So this is just the use the G action, not the cross braiding. G action. Okay. And after you define all that, you just have to, and then at some point you have to define an interchanger. The interchanger that you define comes from the G cross braiding, right? Because the interchanger is part of the whole gray monoid that you're writing down. Okay, but that comes from the G cross braiding. And then your task is to show that all of these things, you know, that really you're actually getting a construction. And moreover, you can do this on the level of higher morphisms. You can do it on, you know, if I've got these gray monoids, these things form a 4 category. So there's 1 morphism between them, and 2 morphisms between those, and 3 morphisms, and 4 morphisms. And you have to be able to do some kind of strictification to get rid of some of the layers. And then you have to have these, you have to be able to do things with higher morphisms and go back and forth. And so there's a lot of that. And so I'm not going to get into all of that. I was going to spend the last, 15 minutes or so of the talk. I'm assuming it's like 55-minute talk, hour talk, something like that. Is that right?
Yeah.
Yes. Okay.
So I was going to spend the last 15 minutes doing this kind of strictification thing, but I want to go one level down because it's quite a lot, trying to do it for this level, trying to do the strictification for this, it's horrendous. It's really quite hard. Especially at the level of objects, you have to use some really technical results in the literature. But if I go one level down, you can really see it hands-on. You can really see the whole thing hands-on. And that's what I kind of want to explain, to just kind of show you how this can work. So what I want to do is I want to give you a proof, at least, of this fact that 2 categories with 1 object are the same thing as tensor categories. Now, it's pretty obvious at the level of objects this is true, but I want to prove something a little more deep than that. I want to show that the collection, the monoidal category is C. This is a 2 category with monoidal functors and monoidal natural transformations. And then I can consider the collection of 2 categories equipped with 0 connected 2 functor star to C prime. So I have to tell you what 0 connected means. 0 connected means all objects in C prime are equivalent to the image of star. Star here, this is the trivial 2 category. It has 1 object, 1 morphism, 1 object, 1 morphism, and 1 2 morphism. It's just like the most trivial thing that you have, okay? This whole thing, 2 categories equipped with 2 functors, this is a 3 category. And I'm going to explain why this 2 category is equivalent to this 3 category. So this really means that that monoidal categories are really the same thing as 2 categories with one object in a very strong sense. Not just at the level of objects, but really the whole collection of them. Really, you can really do that. So this 2 category is called, we'll call it moncat. And over here, this 3 category, I'm going to call it 2cat star. Okay, because I had 3cat G before, this is 2cat star. So these pointed 2 categories. Now, how does one go about proving this? Well, what you do is, first of all, you use McLean to say that this is the same thing as the 2 category of strict monoidal categories. And what I'm going to do in the remaining, 15 minutes is show that this is equivalent to a 3 category called 2cat strict. Okay, so I'm going to take these pointed 2 categories and I'm going to strictify them for you, and then we're going to be able to see why these things are equivalent in a very easy way. Okay, why this 3 category is equivalent to a 2 category. So I'm going to try to convince you that this is an okay thing, that it's actually a very natural thing to have happen. Okay, so to get into this, I want to tell you more about 2cat star. What is 2cat star? 2cat star, it's a 3 category. The objects are pairs of a 2 category and this 0 connected 2 category. Okay, so the 0 connected 2 functor from the trivial 2 category into C. So what I'm going to do is we're going to write 1 sub C is the image of the identity of star. Okay, that's the idea. Great. 1 morphisms in this category. Well, it's a 2 functor from C to D, but it has to be compatible with the pointings. What does that mean? It means that, well, C came equipped with this pi C, and D came equipped with this pi D, and A fits in this nice little triangle. And so what I'm going to need is some natural isomorphism alpha that fills this triangle. Okay, this is this extra data that plays well with pointings. And this is what's going to cause this whole 3 category to collapse later on, is that this extra data I'm bringing around. 2 morphisms. Well, a 2 morphism here, it's a natural transformation from A to B together with an invertible modification. We're going to call this thing M, right? That this M here is my invertible modification. And what does it do? Well, it helps you fill the following. It's a map that does the following. I have my pi C to C. I'm going to write here B going down to D. Here is pi D. And this is my beta, because that's this part of this second functor. And then I could also have over here, I have pi C, I have pi D, here's D, here's A, here's B, here's my eta, my natural transformation, and here's my alpha. That's an isomorphism. This M is meant to be a modification. This invertible modification goes between these 2 things. Again, it's this data that's making all the pointings play well together nicely. That's what these extra things are. And the 3 morphisms, well, it's some modification. Okay, it's this modification P is going from eta to zeta. It's a modification, and it's satisfying. Well, if I take pi D, then A circ pi C, and down here I have B circ pi C, and I have a 2 morphism here, and I have a 2 morphism here, and a 2 morphism here, which my the first 2 morphism is just this thing is alpha, that thing is beta. Over here I've got zeta circ pi C, that's what you would call that, and here you would write N. Right, this is this morphism here. Okay, this should be the same thing on the nose as, here's pi D, here's A circ pi C, here's B circ pi C. That's alpha, that's beta, and this goes around the outside. This is again zeta circ pi c. Over here I have eta circ pi c. This is my 3. This is my p circ pi c. This is what p is doing. And over here, this is my m. That fills that. These have to be equal on the nose because I'm at the top level. Okay. So that's what this 2-cat star is. It's basically these pointed 2 categories with one object, but you're carrying around this extra data that's meant to like take these pointings and play well with it. And the theorem is 2-cat star, these pointed 2 categories, is equivalent as a 3 category to the full 3 subcategory, what the full, okay, it says full at the level of 3 morphisms, 3 subcategory, 3-cat point, I guess. Point is what I'm writing down here. So what is this meant to be? So first of all, I'm going to write this down in another color here because I have to, we're going to go back in this color to change things. Okay. So what is this 3 subcategory? Here, I want to let these 2 categories be strict. So I'm only going to take strict 2 categories. This should be strict. Let's make this the strict one. So strict 2 categories. Instead of 0 connected, I want 0 surjective. Okay, so I'm really hitting that's saying it's a strict 2 category with only one object. And it's hit by this 0 connected 2 functor. And I want that 2 functor is of course, yeah, that's going to be strict 2. We can strictify that 2 functor. Down here, at this level of 1 morphisms, I can require that A of the only object of C is, of course, the only object of D because there was only one of them. Because in this point, these 1 morphisms here, I'm assuming that both of these 2 things are the strict things that I just had above. So now I'm going to require this. And I'm also going to require this alpha. Alpha has a component of this star. I just want it to be 1 sub D. And alpha 1 sub star is going to be A star 1. This is like some extra condition here, which, but this is basically saying here, this transformation, right? Transformations of 2 functors kind of act like these half braidings. They can have these extra invertible objects around. And this is saying that this transformation, this invertible object associated with the transformation, I can take it to be the identity, okay? This is the difference between monoidal natural transformation and a 2 transformation between 2 functors, because you could think of a monoidal functor between monoidal categories as a particular kind of 2 functor. And then you might think, well, a higher map between it should be some kind of 2 transformation, in which case I should expect kind of like these half braiding type things happening. But this is saying, no, you don't have to worry about the half braidings. It's just the identity, okay? Here, down here for the 2 morphism for the point, this strict subcategory, here, if I can make such that, again, eta star is just the identity, and what else am I doing here? Eta, what am I doing here? And, oh, and M, sorry, that should be M. And M is the identity of 1 sub D, okay? So in some sense, all that's left is, this is saying all that's left of my 2 transformation is just the monoidal natural transformation part, because the eta star is the identity, the modification goes away, and that's all the data that's left is that monoidal natural transformation. And then here I'm taking all of the 3 morphisms. But it's going to turn out that there aren't any 3 morphisms besides identity morphisms in this strict category, okay? And so you can actually prove it, okay? On objects, well, this is easy, actually. Just use McLean to strictify those 2 categories. It's not so hard. And now, if I'm given this nice 2 functor, I want to find this other nice 2 functor that does what it's supposed to do. Well, the idea is, what I want to do is I want to take that x, CD, and I'm going to protect it with these. I'm going to hide this alpha star inside this alpha here was not necessarily I'm basically hiding the pointing inside there by putting this protective thing. And I can do the same thing inside with the unitor, and the same thing with these compositors here. This is A of C, this is A of D, this is A of C tensor D. Up here, this was A of 1. And here, I'm just going to protect around like that. And this, I'm going to protect here. Okay. And you just write that down, and you have to show now that that's a 2-functor, but you know, the picture, if the red thing is a 2-functor, then this thing is a 2-functor. But then you actually have to construct an equivalence between A and B via some other higher transformation. So again, you kind of hide this extra thing that can possibly be in this transformation. You hide it inside the equivalence. And here, what does this look like? It should look like some kind of half braiding. Here I have alpha star. Here's alpha star again. This is this half braiding where I've got this half braiding with an invertible object there. Here, I'm going to have this A of C going through. So you'll notice here, this whole thing here, that's B of C. So here you're seeing this nice transformation with this invertible object here. It's a transformation between B of C and A of C. Basically, it's going between B and A. This is exactly telling you that A and B are going to be equivalent things via this invertible transformation. Okay, so that's how you strictify 1 morphisms. And you can do 2 morphisms and such things too. You can, I guess, this isn't so bad. The idea here is you can just take this to be 1 sub D, and gamma C you can define as, this is zeta C. The idea is if you have a transformation, I'm going to define another transformation where this modification is just the identity. You can get rid of that other part, and you do it as follows. You just kind of you take, basically you're gonna hide the modification inside your definition. It's kind of the same principle. You take the thing that you want to get rid of, and you hide it in the next definition. Okay, that's kind of the idea here. So maybe I kind of hid that with this blue. This one should have been blue. This is kind of the thing I'm hiding. And you can check that this is just gives you a definition here of another transformation and modification, and things just kind of work for 2 morphisms. And you're taking all the 3 morphisms, and then you just say, okay, well that works. That gives me this nice 3 subcategory that's equivalent. And the last thing you want to do is you want to show for this, I guess we call it strict, not point. This is 2 truncated. There's only identity 3 morphisms, so it's equivalent to a 2 category. So in order to do that, essentially, you just you can just do this in string diagrams. The idea is that when you write this, you write this defining condition that happens at the top. When you end up writing this, what happens is that, sorry, that's n star. This becomes n star. And I'm drawing this by taking just something formally dual to I'm taking something dual here. So this is n, and this is the string diagram looks like that. That's this. Right. That's the diagram is dual to these other pacing diagrams. So here I have beta star, right? Because this was beta, this is alpha. This here is alpha star. This over here is zeta star. Okay. And then over here on this side, this just has to be equal to M star alpha star. So let's put P here, eta star, and then zeta star. Down here is beta star. But because we already showed that we're in this nice strict subcategory, alpha star is beta star, is eta star, is rho star, and they're all just one. We could just take them all to be one. And moreover, we knew that M star is N star is the identity of 1 sub D. So everything else is an identity. It's just not there. And this just implies that P is the identity. There's nothing, it's the identity of 1 sub D. There's nothing else to do. And finally, to show that really you have to show eta is zeta. Just because this happens to be identity, it doesn't mean that it's an identity 1 morphism. It just means somehow it's an identity map. You have to you can show here that you use the modification relation. Modification relation says that I have this. It pulls along the other side of this. And since this is the identity, it's just not there. This is the identity. It's not even there. This is saying exactly that eta C is zeta C. For every C, that's just saying eta is zeta. So it is, you know, this 3 morphism was an identity 1 morphism. Okay, or sorry, this 3 morphism was an identity 3 morphism. Okay, and then you finally show that really these are equivalent 2 categories. In fact, once you take a proper truncate, it's really they're isomorphisms of 2 categories there. Okay, so yeah, I'll end there. Thank you very much.